So if you look at the syllabus thing, it should actually list the test. It's not accessible yet, but it should show up as like pending for Friday, Saturday, Sunday, Monday. It should go live at about midnight or 1 minute after midnight on Friday morning, and then be available all the way through until midnight on Monday. Remember that once you log in, you have a 4-hour time block in which to complete the test. I'll talk more about this again on Thursday, but hopefully everybody's actually seeing it as an upcoming event on their syllabus up at this point, I think. It seemed to work okay when I did it back in the spring semester of like putting it into the system, but actually having it not go live until a certain point. So since I had lab yesterday, I brought my ions home with me. See if this actually works. All right, my pretty pictures. Okay, I want to talk about nomenclature again for just a moment. I had drawn some pictures on my funky little whiteboard last week, I guess it was. And so actually, here are my ions. So one of the things that's sort of visible about this is, since this is potassium, and note that it has a single point on it, which is supposed to be representative of the fact that it has a +1 charge under most circumstances. And then I have a chlorine, chlorines being halogens, like to usually be -1. And when you see the two of them together, you can kind of see that there are no leftovers. There are no points left over. There are no chunks cut out left over. This is a visual system that I did not invent, okay? This is something that is available in little magnetic stickers that people can, like, I guess, put on their fridge or something. I took the idea and recreated it on a much bigger scale. Normally when I lecture from the board in a classroom, I made them specifically a lot bigger so they can be seen when they are stuck to the board. So let me pick a different one. All right, here we have strontium. Strontium's an alkaline earth metal. If I try to set this up in such a way that my strontium only has a single chloride attached to it, you can see that there's this empty point here that's not covered up because I don't have any other atoms available at the moment to cancel things out with. So let's see if I can do this here without making too much of a mess in reverse. Okay, so if I've got strontium and 2 chlorines, then I end up back with that whole situation of I don't have any leftovers. I have just enough chlorines, or chlorides in this case, to accommodate the fact that my strontium has a +2 charge. Like I said, we're back to kind of nice visuals to help you maybe get a little bit better grasp on the idea that things have to match. You just made a nasty face. How about strontium and sulfur? Sulfur is under oxygen on the table. Oxygen likes to be -2. That means sulfur likes to be -2. This is a case where, since my sulfur has 2 cutouts, I can use just 1 atom of sulfur and just 1 atom of strontium and actually end up with a neutral molecule. So sometimes you have a 1-to-1 ratio, sometimes you have a 1-to-2. We also spent some time talking about see if this actually cooperates here. The fact that my transition metals often occur in more than one option. I made 2 different coppers. I have a copper 1, because it has 1 point on it. I have a copper 2, has 2 points on it. I go back to sticking things with chlorides again. I have to find my other chloride. So I've got the 1 version, which is just a 1-to-1 option. But then I've got a different version of copper, a copper 2. If I have copper 2, it needs 2 chlorines. Again, visuals to kind of accompany the idea that having a copper atom is kind of insufficient information. If you have a transition metal, you need to know which version of that transition metal you are dealing with. Otherwise, you can't figure out how many negatives the anions are going to match up with it. Like I said, I dragged this home from work so that I could hopefully give you some better visuals than my weird, really not great drawing on my little whiteboard thing.
Question.
Yes.
So if you write that right on the board, right? If you write, you got copper, and then you have the you had the copper, then you had the 2 chlorines. So that would be Cu, then Cl2. How would you write? Okay.
Because so Cu, there is no 1. If you see the element symbol, you are assuming you have 1.
Okay.
And then Cl2 to indicate that you have 2 chlorines available to go with your single atom of copper.
Okay.
Otherwise, you get a different molecule. CuCl is copper 1 chloride because it only has a single plus charge on your copper.
Okay. I like that. I wish I had that because I could use that.
I have a paper version that's designed, it's not designed for transition elements. It's actually designed for alkali metals and alkaline earth metals. I actually designed a paper version back when I taught high school for a while. And I actually have used it with my co-op students when I teach for the homeschool group. It's not a digital file though. I'd have to scan it. Let me think about that. Maybe I can find a way to scan that and upload it so that if you want to cut them out and paste them together, it might be helpful. I'll look into that over the next day or 2 and see if maybe I can find a way to do that. Because like I said, I have a paper version of it. It's not transition elements though. Somebody else had a question.
Yeah, actually 2 questions.
Okay.
One is it ever possible for different charges of the same element to exist in a molecule? If you have a complex molecule, like could a copper 2 exist with a copper 3 just in different places within the molecule?
No.
No. Okay.
Even when you have what are known as coordination compounds, you only have a single charge assigned to your element at one time. Now, if you have more than one molecule, all bets are off. But for a single molecule, you cannot mix.
Okay. And my second question, that first example you showed us with potassium and chloride there, where there was just 1 and you had 1 missing. Now, let's say you're out in nature or whatever, you have another ion with the same charge as chlorine, right? They're swimming around together and there's that 1 open spot on the copper. Is there a rule as to who beats who out for binding with the copper with that -1 charge, or is it
No,
just kind of
not
first come,
really.
first serve?
Not really. It's actually based upon, I guess you could say loosely based upon concentration and availability. In an upcoming chapter, we will do precipitation reactions. And precipitation reactions, you have a beaker full of options and you have to pick them in such a way that you create neutral molecules. There's a second semester topic that actually allows you to figure out who wins based upon a value known as KSPs. That is not a first semester chemistry topic. That is a second semester chemistry topic.
Happy to leave it
Does
there.
exist. There is a mechanism for that. We haven't got there yet.
Okay.
Other questions regarding nomenclature stuff? Since we kind of finished up the chapter, lots of people have turned in their homework in the past day. I started grading them. I haven't finished grading them yet. It's due before midnight tonight. I will try to make sure I get them all graded tomorrow, and then toward late afternoon, evening, I will post the answer key for the chapter 2 homework set so that we can then go over the chapter 2 homework set answers on Thursday, and also talk a little bit more about the test. I can't spend the whole Zoom doing that on Thursday, but we are going to spend some time working on that prior to you having test this weekend. Other questions?
Professor,
Yes.
I don't know if it'll be as helpful for other people, but there was a website I used in high school to learn nomenclature, and I put the link in the chat if anyone wants to check it out. But it has different levels, so you can start at high school and then move up to university level, and it just gives you a chemical equation, and you have to name it, and it gives you pointers on where you went wrong as you go. I used it in high school, so I just figured if anyone else wanted to maybe try it, I put it in the...
Definitely, if you guys want to have a look at that website. The one that I had suggested was Memrise. There's a couple of different sites that give you kind of drill practice. So yeah, any of them that you find helpful, definitely use them while you're working on homework, while you're practicing prior to the test, because remember, the lockdown browser is going to be in use during the test. So once you log in, it freezes your ability to look stuff up. But definitely prior to doing the test, use whatever you find the most useful. Lab book, textbook, websites, all that sort of thing. Actually, I'm not familiar with GeoExchange, but yeah, whatever seems to be helpful while you're working on this. Other questions? All right, we are going to switch gears then, since we have a finite number of weeks to get through all of this. Let me find my screen share thingy. All right, this should be chapter 3 notes. We're actually kind of hitting a couple of points again that did pop up somewhat in the previous chapter. The idea of isotopes and some of the ways to deal with them. So, way back in the dark ages when I was in high school, one of the things that all the textbooks said was, you can't touch an atom. Okay, you can't touch an atom directly. All bets are off now. We have technology known as scanning tunneling microscopy. And we have technology known as atomic force microscopy. And you can utilize the technology to move atoms one at a time. And I need to post the link. Okay. There is a YouTube video called An Atom and His Boy that lasts about a minute and a half. I need to find it and post the link so you guys can watch it later. That is, or was created by IBM, IBM being still a tech leader, that did a stop motion animation, little video, little cartoon, using individual atoms of silicon. I think they used a total of about 50 atoms complete in the creation of the video. It's a really cute video. And by the time you grasp the idea that they took a picture, used their atomic force microscope and nudged all of their little atoms around, took another picture, all of those things, if you look at that, the idea that they did it with all these individual atoms is really kind of amazing. Like I said, it's a stop motion animation thing, lasts about a minute and a half. So anyway, what if normally you can't touch things? Okay, we're coming up toward Halloween. I guess Halloween technically still happens, even though I don't think the trick-or-treat thing is probably gonna like actually do this year. But it's really typical for places in the past to do contests. How many M&Ms are in the jar? What if you couldn't touch them, but you had some information? What if you knew how much an average one weighed, and you had some information that told you how much the whole batch of them weighed, minus the jar? You could probably make a pretty good guess. So I created some fictitious data here. I said, if your M&Ms weigh about 1.23 grams, and the whole bunch of them that's in the jar weighs 358 grams, you could do a division, put your total divided by your individual one, and you could probably make a pretty good guess. There are likely to be 291 in the jar, given, unless there's one that's really huge or unless there's a couple of broken ones, you could probably come out pretty close to the same height, to like an accurate assessment. Why do we even kind of go down this route? Well, back to the idea that under normal technology levels, we can't really touch things individually on the atomic level. This leads us to AMUs. Word that means a phrase, atomic mass units. We looked a little at isotopes in the previous chapter. We can see there a carbon-12 atom. So it is the isotope 12 of carbon. If you took that particular atom or that particular isotope of carbon and you whacked it into 12 equal pieces, that is essentially what the mass of one AMU is. Now, granted, if you're talking about AMUs, you're probably not going to want to use that particular unit unless you're only dealing with one atom, maybe a couple of atoms. You don't want to deal with billions or trillions because then it becomes an unuseful unit of measurement. But let's go back to the weighted average idea. Weighted averages have lots of uses, including calculating your grades. I looked up tungsten. I mean, technically speaking, tungsten has about a dozen isotopes. I picked essentially the 5 that are the most common because I didn't want to give you a list that had all 12 isotopes in it. So I just picked those 5. We've got everything from the somewhat lightweight one, tungsten 180, which only has 0.12, which is less than 1%. We've then got 182, 183, 184, and 186. They're a lot more common on the whole there. We've got a 26.3% one. We've got a 14.3% one. The one that's most common is the 184, so 30.7%. And we've got a 28% one. Remember that when you are doing weighted averages with isotopes, you are multiplying the mass times the percentage, which then also means you must move your decimal place. If we looked at, for instance, the last one in the column there, 186 times 0.28, since a percentage is out of 100, you're moving your decimal 2 spaces. Multiply across, and then total them. Another thing to keep in mind for weighted averages have no division step. Unlike regular averages where you count up how many things you've got and then you divide by that number, there is no division step when we are doing weighted averages. You do a totaling. All right, back to AMUs a little bit further. We don't want to use AMUs in the lab. Okay, everybody, regardless of whether you have me or whether you have somebody else, everybody should have done one lab at this point, because my Monday people who got caught in the Labor Day thing where they didn't have lab until yesterday, we were the last lab of what amounts to the lab rotation, the 2-week rotation. Everybody should have had one actual physical lab at this point, and had a little bit of experience then at using the balances. Balances are grams. Balances aren't AMUs. AMUs are unbelievably tiny. Therefore, we're not using them in lab. We're going to have grams and moles. So now we get back to the whole concept of what a mole is in terms of chemistry versus biology. Of course, in biology, a mole is the little thing that digs up your garden or digs up your front yard and makes holes. If we're doing chemistry, a mole is a value that, or is a word that has a number value. So in the English language, we've got various words that mean a particular number. So dozen in English means 12. If you go to Office Depot and say, I want to buy a gross of ink pens, gross means 144 in terms of counting. You could say, I want a ream of printer paper. I believe I'm correct in saying a ream is 500 sheets. So mole actually has a number value. It has a huge number value. 6.02214, we actually usually use a slightly rounded version of that. We usually don't keep the 1 and the 4 when we're doing the math problems. Times 10 to the 23rd. It also is actually equal to how many carbon atoms are in 12 grams of isotope carbon-12. Other trivia things to kind of give you an idea. If you had a mole of water droplets, you could take a shower for about 100 billion years. If you had a mole of the little marshmallows like they put in hot chocolate, you could make a line from here to Pluto and back, somewhere on the order of 500,000 times. But on the other hand, 1 mole of water molecules is 3 teaspoons. That kind of gives you both ends of the situation there. It's a number, but depending upon whether your number is referring to a sub-microscopic thing, or whether it's applying to a tangible, you could actually pick it up with your fingers kind of thing. There's a big size difference there. One of the things that this makes useful in terms of applications then is when you look on the periodic table, the number that we have been referring to as the atomic mass, which for most elements has decimals in it. We talked about why it has decimals in it in the last chapter. That particular number tells you how many grams are in 1 mole of that element. And I gave you 2 examples here. If you have iron, and you look at iron on the periodic table and it says 55.85. Well, if you had 1 atom of iron, it would weigh 55.85 AMUs. If you have 1 mole of iron, same number, 55.85, but it's in grams. Something that you could actually, without great deal of difficulty, weigh in a lab situation. How about lead? Well, lead's a lot further down the periodic table. Lead is 207.19. So a mole of lead weighs a lot more than a mole of iron. So we need to kind of use all these ideas to begin to do, and yes, dimensional analysis kind of comes back to haunt you yet again, different ways to interconvert a whole bunch of different units back and forth. The first one we're going to look at is going from moles to grams. How much does 0.38 moles of aluminum? All of this revolves around using the periodic table a lot. You're using different information than you used predominantly in the last chapter, where it was symbols and names for the most part for chapter 2. Now we're using a lot more of the numerical information from the table. If I look up aluminum, it has an atomic mass of 26.98, and I'm going to set it up so that it looks like a dimensional analysis unit here. I'm going to put the 26.98 grams over 1 mole. That way, when I multiply the 2 things together, the 0.38 and the 26.98 grams per mole, the moles will cancel out because one's on the top and one's on the bottom. And I have an answer of 10.252. If I was paying attention to sig figs, I probably should actually round it to just 10 grams, 10 with a decimal point after it. But I made all of these examples kind of match the fact that the balance we use in the labs weighs to 3 decimal places. So I'm trying to kind of get everybody used to the idea that when you're applying these to laboratory and real world situations, you're usually using 3 decimal places to report your values. So I gave you 10.252. How about going back in the other direction? Starting with grams, going back to moles. If I have 20.4 grams, and I want to know how many moles that is, I'm still looking back on the periodic table. I need to look up barium in this case and find out what atomic mass is actually linked to that. Barium is a lot bigger than aluminum. It's 137.34. Note, my conversion factor in this particular instance is flipped because I want my grams to cancel out. I'm going to do 20.4 divided by 137.34 to find my number of moles. I did sort of stick with sig figs, just for convenience sake for this particular one. 20.4 is 3 sig figs. My answer's in 3 sig figs. 0.149 moles. Now, what if you're doing something that wants you to go from atoms all the way to grams? You have to do this in 2 steps. Now, granted, you could do it in 2 linked steps. I did the example here in 2 separate steps. You could link the 2 of them together and make it 1 extended step. It doesn't actually make a difference mathematically. 2.89 grams of gold. Gold is heavy. Gold is heavier than barium. 196.967. The first step involves going from grams to moles. So I divide, I get 0.0147. Now I need my magic number. I need the 6.022 times 10 to the 23rd. That's how many items are in a mole. Multiply your moles times that value, and you get 8.83 times 10 to the 21st. Now here's something to keep in mind. Even if you had a milligram of a substance, you are still probably going to end up with a number of atoms or molecules that has a fairly large exponent, probably at least in the teens, if not in the 20s. So if you are doing this 2-step conversion, then that's allowing you to, and I know that somebody posted something in the chat and I'm like trying to let it make me, I'm having tech problems here. I'm trying to see what the chat says and it is not showing it to me. Let me do stop share. Oh, okay, maybe it was just technical difficulty stuff. Okay, let me go back to share. All right, but anyway, even if you have a very small gram mass, you're still going to have a monstrously huge number of atoms or molecules. So these 3 examples did it with an element. Obviously, kind of like the nomenclature stuff, first we named elements and then we started sticking them together and making molecules with them. The same idea kind of sort of applies here. You can do the same thing, same types of calculations, but instead of doing them for an individual element, you can do them for a molecule. Now there's a couple of different names that are applied here. And if you're looking for YouTube videos to help you with problems and that sort of thing, the names you might see molar mass, which I think is the one your textbook likes the best. You might see molecular weight. Okay, all the textbooks I used when I was working on my bachelor's degree and actually on into my master's degree, they tended at that point in time to really like the term molecular weight. It means the same thing. It just, these days, a lot of the textbooks and websites tend to use molar mass a little bit more frequently. You also might see the term formula weight. Or here's another one that I'll throw out there that you might run across, gram formula weight. And they use 3 words rather than just 2 words. They all kind of mean the same thing. They all basically are done the same way. I gave you a big molecule here. Now note, I set it up in a particular way. You don't have to do it this way, but I have a reason. By setting it up first as a list of the elements, so I'd like write iron, sulfur, oxygen, downward, make a column out of them. Then I write how many of each one: 2 of the iron, 3 of the sulfur, 12 of the oxygen. Back to the periodic table. Look them all up. I've got the 55, and I actually grabbed an extra decimal place with me when I did the iron, 55.847. I used 32.064 for my sulfur, and you will also see this true in many textbooks and examples. Some of the periodic tables will list oxygen as 15.9994, I think it is. However, a lot of example problems will go ahead and round it. I believe your lab book periodic table has the rounded version listed as just 16, as opposed to 15 with a batch of 9s after it. I have a tendency to use a 16. It makes such a minute difference in the final answer. So I made my list. I looked up my values. I multiply across first. So 2 times 55.847 gives me 111.694. The 3 sulfurs times my 32-ish gives me 96.192. 12 oxygens times 16 gives me 192. Add them all up, and this tells me my rather large molecule, if I had a whole mole of it, would weigh almost 400 grams, 399.886 grams. Like I said, there's a reason for this. As we get deeper and deeper into this chapter, you'll kind of see why I have a favorite method for how I set up calculating my molecular weight. There are useful ways for why it should be done this way. It can be done another way. You can just hammer it all into your calculator. That doesn't make a difference, but doing it this way has some advantages. How about tying some things together? Caffeine, one of my favorite molecules, has only 4 elements in it: carbon, hydrogen, nitrogen, and oxygen. If you look up the formula, and we'll talk later a little bit more about empirical formulas. In this case, it's actually a molecular formula, not an empirical formula. I've got 8 and 10 and 4 and 2 for my actual values here. So 8 carbons, 10 hydrogens, 4 nitrogens, 2 oxygens. Back to your periodic table all over again. Look up your values: 12, 1, 14, 16. Multiply across. I get 96 for my carbons, a little over 10 for my hydrogens, 56 for my nitrogens, and 32 for my oxygens. So 1 mole of caffeine weighs 194.2 grams. One thing you also might notice here is I dragged a whole bunch of decimal places with me for doing the hydrogen. If you rounded your hydrogen to just 1, it will not significantly change your answer. It will only change the value after the decimal point. So if you rounded it, it would not give you something very different. So here's some things that tie together then. If I have a cup of brewed coffee, not the evil Keurig crap, it has 300 milligrams of caffeine. How many molecules is that? So I'm going to do it in steps. And I realized, because of course this is a file and I'm actually used to writing this on the board, my 194.2 that looks like it's written under the 0.300 grams actually should be slid over about a half an inch. It should be 300 milligrams is 0.3 grams, because I want to convert from milligrams to grams as my first step. Then I'm going to use my molecular weight. I'm going to have 1 mole over 194.2. Like I said, it's kind of misplaced a little bit here in the file. That will give me 1.55 times 10 to the negative third moles of caffeine. And then I pull that one additional number into the problem of the number that matches mole, 6.022 times 10 to the 23rd. I have a final answer of 9.33 times 10 to the 20th molecules. Kind of roughly, you get one molecule of caffeine for every cell in your body. Roughly, not exactly. All right, now we begin to head in the direction of why I tend to set things up a specific way. So this segment of the chapter dives into, I guess you could call it analysis of molecules. If you put the atomic mass of one element over the mass for the whole compound, we're talking molecular weight / molar mass here, and then you multiply by 100 so to get a percentage and not a decimal. Again, there are different terms depending upon which textbook you grab. Some of the textbooks like to call it mass fraction. Some of them call it mass percent. I probably call it percent by mass most frequently. You could also call it weight percent. They're all the same thing, okay? It's a ratio of parts to whole turned into a percentage. All right, back to more example-y things. Now we get into the whys. So in order to have the number that goes on the bottom, I need to do my total. And I'm doing it here for a molecule of silver 1 sulfate, Ag2SO4. So first I made my little grocery list. 2 silvers, 1 sulfur, 4 oxygens. Then I did periodic table stuff. 107. Since I only had a single sulfur, I just kind of wrote it there on the other side of the equal sign. 32.064. 16 for oxygens. And I multiplied across. 215, 32, 64. You get a total of 311.804. Now here's the why. Note, by setting it up by this method, I've already done half my math work. Because if you are doing percent of silver in this molecule, you have to account for the fact that there are 2 atoms of silver, not just 1. And so because I already multiplied that little bit out, it actually helps me because I can then grab my 215.74 and slam it on the top of my fraction. I've already done that part of the math now. Put my 311.804 on the bottom, divide, multiply by 100 so that it's a percentage and not a decimal, and I get 69.19%. Same thing then holds true with my sulfur and my oxygen. Now I only had 1 atom of sulfur, so it doesn't really gain me a lot in terms of looking at my sulfur atom. I just grab the weight of that 1 single sulfur and put it on the top, 32.064. Same number on the bottom, because each and every portion of this problem, I am putting the weight of the full molecule on the bottom, 311.804. Divide, multiply by 100, I get 10.28%. Now I go back to a little bit of an advantage here. I already multiplied my 4 times 16 to get 64. Grab that number, put it on the top, put your 311 on the bottom, divide and multiply, and I get 20.52. Now granted, and you'll see my note there, if you actually go back and put these in your calculator, if you go back and you put 69.19 and 10.28 and 20.52 all into your calculator, you don't actually get 100 because I rounded just a little bit when I was doing this. I get 99.99. But if you round that up, you get 100. So it's also a check step. If I add all the percentages for all of the elements in my compound, you should get essentially 100%, give or take a tenth for rounding. So then I did a different one here. We've got KClO3, potassium chlorate. ClO3 is the chlorate polyatomic. I only had one potassium, I only had one chlorine. I do have 3 oxygens, and yes, I didn't write my 16 in there. I kind of shorthanded this a little bit. 3 times 16 is 48. The whole thing ends up being 122.6 for the entire molecule. And again, I kind of like shorthanded this a little bit to do the rest of the answer key for this particular problem. You end up with 31.9% for your potassium. You end up with 28.9% for your chlorine and 39.2% for your oxygen. If you total them up and given rounding and all that kind of thing, you get your 100%. So back to the reasons and the why I set it up that way. Okay, back to the beginning of the pages for this notes file. As I began to do my molar masses / molecular weights, I did set them up in the particular way because of this type of analysis. By setting them up in that method, it helps you along the pathway toward doing the math for these types of problems. What about ratios? We're going to dump a couple additional buzzwords in here. Empirical formula. Empirical formula is kind of like lowest terms when you're doing fractions in math. You could have 4/8 or 2/4, but they both reduce down to 1/2. That's kind of what the empirical formula does to you. It gives you the ratio, but it gives you the ratio in the smallest terms possible. Molecular formula gives you the exact formula. So back to my caffeine problem for a moment. One of the things I said about my caffeine problem is when I wrote it out, it was actually a molecular formula, not an empirical formula, because I hadn't reduced it. If you go back and you look at the caffeine molecule, they're all even numbers. So look at the one that I have here that says C6H6. That's actually a molecule that will come back again later. C6H6 is a hexagon. If you attach all of your 6 carbons around in, well, it's not actually a circle, it is a hexagon, and you put these 6 hydrogens out like kind of spokes on a bicycle wheel, you end up with this roundish molecule known as benzene. Benzene has some really unique properties, and we'll come back again to that particular molecule later. But C6H6 is a molecular formula. I could reduce it down. And again, remember, I'm not showing my ones, the ones are implied. If I divide both of those by 6, I get a 1-to-1 ratio. I get just CH. The CH is my empirical, the C6H6 is my molecular. How about the one below it? It has all even numbers. I've got C12H4, Cl4O2. Well, if I divided everything through by 2, I get C6H2Cl2O, because there's only a single O left once I'm finished with my division. So having all of the even numbers, 12, 4, 4, and 2, that's my molecular formula. The 6, 2, 2, and 1 is my empirical formula. It is my ratio. There is a lab that we actually do not do currently as part of our lab rotation that involves magnesium and oxygen and empirical formulas versus molecular formulas. Way back before mass spectrometry, which is a very, very massively expensive piece of chemical instrumentation. If you watch CSI or other sorts of things like that, and they go, oh, well, I identified the white powder and I know that it's cocaine or something like that. And they did it by sticking it in a machine. What they're actually using is a mass spectrometer, okay? You can do a lot of things, however, by, we'll call it the brute force method, that doesn't involve instrumentation, that involves glassware and balances. And you can find a lot of the same information, it just takes a lot longer. So I gave you one here that involves lead and chlorine. I gave you 0.6884 grams of lead and 0.2356 grams of chlorine. You're told that it makes a binary compound. So obviously the lead and the chlorine are combining and making a molecule. We want to know what the empirical formula is. So backtracking for a moment to the previous chapter that we just finished. Lead, transition metal lead, comes in a +2 version and it comes in a +4 version. So if I didn't know that, I wouldn't really have a starting place, but even if I didn't know that, I have data. And the data will allow me to figure out which version I have. Now we're using some of the same math from earlier in this chapter. We're taking grams and we're converting it over to moles. We've got 0.6884 grams divided by the mass from the periodic table of lead, 207.2, and you get 3.3 times 10 to the negative third. Yeah, you don't have to write it in scientific notation. That's just sort of an optional event. Same thing with your chlorine. 0.2356 divided by the periodic table weight, 35.45. I get 6.6 times 10 to the negative third. Now that one you can kind of eyeball. You can go, oh, I've got twice as much chlorine. You can also set it up and make a fraction out of it and confirm it. 6.6 to the third, negative third, and 3.3 to the negative third on the bottom. You have a 2-to-1 ratio. I have a +2 version of lead in my compound, PbCl2, because I have a 2-to-1 ratio in my data. What if you had more than just 2 elements? There's one more step involved. Here's a nice little organic compound, some of the same elements we saw in the caffeine molecule. Carbon, hydrogen, nitrogen, oxygen. And I gave you weights for them. 0.2990, 0.05,849, 0.2318, 0.1328. I'm going to do the same first step that I did with my lead and my chlorine. Let's see if I can actually, yeah, I can kind of show you all of it on one page here as I scroll it. So I did all my division steps. I divided my carbon, I divided my hydrogen, I divided my nitrogen, I divided my oxygen. And each time I get moles. But note, there's one more step here. Once I had my moles, I skimmed through my list of 4 and picked the smallest one. In this case, the number of moles of oxygen. Then I go back and divide each of my moles by that smallest number. Some of them don't come out to be exactly and precisely whole numbers. I wanted to give you data that had a slightly more realistic feel. Obviously, textbook problems are often kind of idealized. I gave you slightly less perfect data here. When I did the ratio of my carbon, my 0.0249 divided by the number of moles of oxygen, I do actually get 3. When I get to my hydrogen and I do that division, it wasn't exactly a whole number, 6.99. I'm going to round that up to 7 because it's really close. I did something similar for my nitrogen. I gave you a value that came out to be slightly more than a whole number, 2.05. I'm going to round that one down. And then the one I started with, divided by itself, has to give you 1. Now, there's a couple of different ways you can write this. Usually, they will write it just in the order in which it's presented. I gave you a list of carbon, hydrogen, nitrogen, oxygen. So unless they tell you otherwise, most textbook problems will expect you to spit back the elements in the same order in which they were presented. So my empirical formula is C3H7N2O. All right, and I think that's where I'm going to end this particular section. And then on Thursday, after we get through some other stuff for review of chapter 2 and all that, then I'll probably continue on with some more chapter 3 so we don't get behind. Let me stop my share. So are there questions about empirical formulas, what we have covered of molecular formulas, or other things? And I noticed that somebody in the chat says chapter 3 notes have been posted. So remember that I reorganized stuff a little bit. The notes are now on a page. All the note files, all the way up to there's a chapter 7 and 8 file that I haven't posted yet, but all of the other ones should appear on a page. Remember, the page thing is really bizarre. It's like you hit the page on the side, the page word on the side, and it looks like you haven't gone anywhere, but there's this little tiny blue box up at the top that says view all pages, and you click on that, and then it gives you an alphabetical list. And there's a page that says chapter or notes by chapter, I think is what I title it. When you click on that page, all the things we've already covered and all the way up except for the very last pair of chapters for the semester should already be posted there.
Got one quick question.
Yes.
Going back through the notes, that's 6.022 times 10 to the 23 molecules per mole. That's a given. That number will always be the same, right?
Yes, that's why I called it a magic number. Okay, it's something that you utilize the same number again and again. Definitely through lots of this semester and even to some degree on into second semester. So yeah, that number does not change. We do use the rounded version. Okay, we don't tend to drag the 1.4 on the end. We use the 6.022 times 10 to the 23rd. But yeah, that number does not change.
Okay.
All of this stuff that we're covering tonight is actually not on your test for this weekend. This is on going to be test 2 material. Like I said, I'm just trying to make sure we kind of keep up because we have 16 weeks and this sort of takes longer than I would like in some ways. Trying to make sure I get everything answered in terms of questions and all that. Anybody have lab problems that you guys need help with before? Because remember, some people will be turning in lab reports. My A group will be turning in lab reports next Monday. Dry lab 1 and experiment 1 and the pre-lab that goes with experiment 1.
One question on the lab. We took that safety quiz online, right?
Yes.
Is that the same quiz? Those the same quiz, the same questions on the dry lab that when you first start? There's another set of true or false. Are they the same, or should we?
There's a couple of them that bear a similarity, but no, they are not the same thing. When I did the online quiz, I just flopped open the lab book and ask you relatively, we'll call it semi-obvious things. If you read the lab book, they are relatively obvious.
Okay.
But they're not an identical set.
Well, I got to go back and do that because I thought that was part. I thought you just copied that and put that into the quiz.
No, they're actually two separate things.
Okay.
If you actually, I know that I have a few people who are still floundering with the getting of a actual physical lab book. If you were to actually look through your lab book and you look at page, I think it's actually page 49, there's a front and back that has this really weird set of instructions that says cite the icon on the front of the page, and then you flip it over and there's a bunch of true false questions on the back. And because I knew people were having a little bit of trouble getting hold of their lab books, I was trying to come up with a digital version so that we weren't quite so dependent on getting the lab book the first day of class. And I also have run into the problem of, because the instructions say something like cite the icon, I have had people draw little teeny tiny pictures in the blank, not realizing that it means you're supposed to put the number and the letter in the blank, like 6B or 18A. I have occasionally had people draw me little tiny pictures, so I was trying to avoid that problem too. But if you have not, I know that there's a few people, I think maybe, who were having trouble getting their lab books. I know it has a due date on that, but I didn't really pay a lot of attention to the due date. Basically, you just have to do it so that I have a grade for that particular exercise. If it took you a while to get your lab book, that's fine. Supposedly, according to somebody who I saw last night, MacArthur's Barnes & Noble has a new shipment of textbooks in, of which some of them are actually supposedly some of our Norfolk campus lab books. So if you have not yet gotten your lab book, hypothetically, there should be some available now. Other questions? If you have not turned in your homework to me yet, remember it's due sometime before midnight tonight. A few people already turned them in and I started grading them. I'll grade the rest of them tomorrow. We will go over the homework set on Thursday and finish up talking about all the things you need to be aware of for your test for the weekend. Okay? Otherwise, I will see you all on Thursday.